This is the Atwood's machine. The purpose of this lab is to determine the acceleration of the pulley system using Newton's laws and compare the values to values obtained from the Logger Pro interface. Alright, so this is the Atwood's machine. Basically what we have here is two masses on a pulley. The one on the bottom now is 300 grams, and the one on the top is 310 grams, 0.7 I believe. So then what's going to happen is we're going to hold it at a certain distance up from the ground, and we're going to drop it, and it's going to move like this through the pulley, and because they're attached to the same pulley and the same string, the tension is the same. So we can then calculate theoretically and using kinematics, and then also using data from the photo gate at the top to find out what the acceleration is in 3 different methods. We can basically compare the methods to find the percent error and find which method is most accurate, comparing it to the photo gate interface.
So now we're going to calculate the acceleration of this system using kinematics. And the way we do that is we first place the heavier mass with 310 grams at a higher height. What you want to do is measure that height with a meter stick, as Kevin will do here. In this case, it is 81.02 centimeters, so 0.8102 meters. So then starting the system at a initial velocity of 0, you then are going to release it and then time the system and get your times, as so. So the timing here was 3 seconds and 3.38 seconds. You will repeat this trial 5 times to get an average time that will be consistent throughout the lab.
Alright, to set up your Logger Pro, you need to go to Experiment, go to Set Up Sensors, and then Show All Interfaces. So then in the photo gate section, you're going to want to click that, make sure it's in motion timing, and then hit Set Distance or Length, and it'll naturally be set to Vernier Picket Fence. And you want to change that to Ultra Pulley 10 Spoke in Groove, because that is the type we are using for this experiment. So you hit OK, and it automatically sets the diameter and everything like that because it's a certain model. So we're going to focus on the acceleration graph for this one, because that is what we are testing for. So basically we're going to collect, and Nathan is going to test it on the other side once I say collect. We're going to focus on the screen for this one because most of it is in that section. Alright, now I'm going to pause the recording there because it hit the ground. And now I'm going to select the area, shade it in the area that we want to measure. I'm going to zoom in real quick just so we can get a better view of it. I'm going to select this area once again. And I'm going to hit the Stat button up here. And I'm going to look at the mean, which for this one is 0.09988. So then we're going to calculate that, and we're going to do this once more, 5 times, and then we're going to find the average there and begin calculations.
So now I'm going to show you the theoretical calculations for the Atwood's machine lab. We will start off first by drawing our free body diagrams of the masses that are attached to the strings. Now you'll want to label the free body diagrams, first with the force due to tension, which is up because it's hanging from a string. This is mass 1. And then with the force due to gravity, which is pulling the mass down. Now we'll draw the mass 2 free body diagram. And again, the force of tension is in the upward position, and the force due to gravity is pulling the mass down. Now we're going to consider up on this side positive, and because it follows the force due to tension on the same string, positive will be down on mass 2. So now mass 2 is actually, in this case, we're going to call mass 1 less than mass 2, as in our experiment. Mass 1 is 300 grams, and mass 2 is 310 grams. Now we're going to write the net force equations for both diagrams. And the net force in this case is just tension minus the force due to gravity in mass 1. And the net force, of course, does equal mass times acceleration. Now we can equal the whole equation to just t, because t is constant on both sides of the diagram. And we'll break up the force due to gravity as well. And so now we just have the mass 1 times the force due to gravity plus, or the acceleration due to gravity plus the acceleration of the whole system, which will equal your tension. Now on the other side, we have the net force is equal to the force due to gravity minus tension, because in this case the force due to gravity is in the positive direction. And again, this equals mass times acceleration. Now what we want to do is you want to break up the force due to gravity so that you only have everything in terms of mass, gravitational acceleration constants, and tension. Now what we can do is we can substitute in the mass times gravity plus acceleration in the first equation, and we'll actually just distribute mass right back into it for tension. So now what we can do is we can distribute the negative sign through and show that mass 2 times the acceleration due to gravity minus mass 1 times the acceleration due to gravity plus mass 1 times the acceleration equals mass 2 times acceleration. Now if you pull out the acceleration due to gravity, g, you'll get g times mass 2 minus mass 1, and then moving mass 1 times acceleration over to the right side, you get acceleration times mass 1 plus mass 2. Now what you can do is you can divide out so that you get just acceleration equals gravity, the acceleration due to gravity, g, times mass 2 minus mass 1 over mass 1 plus mass 2. Now we know that if you know your masses, you can solve for your acceleration of your Atwood system. And because we do know our masses, we can do that. First, we're going to rewrite our acceleration equation. Acceleration equals gravity times mass 2 minus mass 1 over the two masses combined. It really doesn't matter what order you write them in because it is addition. So now we know that our mass 2 is 310.7 grams and our mass 1 is 300.7 grams. Now we will substitute our numbers in, so 9.81 meters per second squared, acceleration due to gravity, and our masses, respectively, 310.7 minus 300.7 grams over the total mass, which is 310.7 grams plus 300.7 grams, which then comes out to be acceleration is equal to 98.1 over 610 or 611.4 grams. So then when you divide that out, you end up with 0.16 meters per second squared as our theoretical acceleration of our Atwood system. Alright, now I'm going to show you the calculating acceleration using kinematics based on the times that we recorded in our experiments as seen before. So first things first, we want to establish that our average time, which we again got from our 5 trials from our previous lab experiments, is 3.79 seconds. Now what we want to do with this is we're going to use it along with our kinematic equations to find the acceleration based on the fact that we know the height. So right here, from which the pulley fell. So here we have our pulley system, and there's our masses, and y is our height. We can define a few things that we know about this. For example, we know that the initial velocity is 0, and so now we are going to look for our final velocity because it is unknown, and we are also looking for our acceleration because once we know our final velocity, we will know our acceleration. Of course, you can solve directly for acceleration, which is actually what we're going to do right now. So what you want to write is that the kinematic equation y, or our distance, equals our initial velocity times time plus 1/2 acceleration times the time squared. Now, using that equation, we can substitute in our numbers. Our distance was 0.8102 meters, which we also knew from measuring in our experiment. And then we know that because our initial velocity is 0, that whole figure will go to 0. And then we are simply looking for 1/2 the acceleration times the time that we know is on average 3.79 seconds. So then when you solve all that out for acceleration, you get acceleration equals 0.113 meters per second squared. And that is how you find the acceleration using kinematics. So now we are going to calculate some percent differences and percent errors based on the accelerations we found using our theoretical as well as our kinematic equations in our experiment and the Logger Pro software with our experiment as well. So first we're going to take a percent difference between the Atwood's theoretical that we found using our free body diagrams and the forces versus our kinematic equations that found the acceleration based on our experimental times. So to find a percent difference, you take the larger value, in this case the theoretical, minus the smaller value, the kinematic, and then divide by the average of the two, and then multiply by 100 to get your percent difference. So we take our theoretical, which was 0.116 meters per second squared, and subtract the kinematic, the 0.113, and then divide by the average, and multiply by 100, and our percent difference will be 34.4%. Now, this is quite large due to friction, but I'll explain that in a minute. Next, we'll take our percent error of our theoretical, once again from the free body motion diagrams, versus our Lab Pro and the Logger Pro software that calculated our actual experiments time, or acceleration rather. And to find a percent of error, you take the theoretical value you have and subtract the experimental one from it, and then divide, in this case, by the Logger Pro, which is considered our our actual value. And then multiply by 100 to get a percentage. So then we plug in the values that we got, and our logger pro was 0.1105, as you can see, and then multiply by 100, or 1106 rather, and then when you do out this math, you see that we had a 44.8% error. And then this once again can be accounted for by friction, but I'll get to that in one sec. Now we're going to take our percent error between our kinematics versus our Lab Pro. And this, again, is the same percent error, theoretical minus experimental. And again, our Lab Pro's experimental value is considered the actual. And then once you do all this math out, by plugging in the numbers once again, you will see that our percent difference, or our percent error, is actually considerably smaller in this case, which again is all accounted for by friction, and we get 2.26% error. So friction can account for all of these percent errors and percent differences because the theoretical does not take friction into account. The theoretical calculations only base their calculations off of the forces acting upon the masses, and because friction only acts upon the string and the pulley, or in between the string and the pulley, it is therefore not included in the masses free body diagrams or the forces that act upon the masses. However, because the kinematics and the Logger Pro both are based off of the data we've collected through our experiment, we know that friction is included because friction exists. The kinematics uses the total time, which is basically, it accounts for the distance traveled over the total time to give you its acceleration, and the Logger Pro actually does measure the acceleration of the spokes of the wheel that is the pulley, and therefore both account for friction. And now you know all you need to know to perform the Atwood's lab and all of the calculations that go along with it. Thank you for watching, and enjoy your day.